So the concept that I'll be describing today is something called total internal reflection, otherwise known as TIR. Okay. Now, something that we want to keep in mind before I describe more of what TIR is that TIR always occurs from a denser to a lesser medium. And what this means is that the N1, the initial medium that the light travels through, will be greater than N2. Okay, that's just something that we need to keep in mind throughout this whole thing. All right, something to illustrate for you guys. Here we have. I'll just draw a little bigger. Now this is the normal. This right here. Okay, as we know, if light travels in this way, and if N1 right here, and there's N2 here, if N1 is greater than N2, what will happen to this resultant light ray? Which way would it go? Would it go towards the normal or away from the normal? As we know, this will actually go away from the normal. Okay, so we have an initial angle here, theta 1. This is actually theta 2, and theta 2 will be greater than theta 1 always in this kind of scenario where N1 is greater than N2. Okay, now that we have that in mind, I guess what we want to know out of this whole thing is what happens when this angle keeps on increasing, this light source keeps on moving this way. What will happen to this resultant angle? What we know is that it will actually come downwards, right? And so what we're trying to find is at what angle is theta 1 equivalent to the point where theta 2 is equal to 90 degrees. So what we're looking for is something like this. We have this here. Here's our normal. Okay, we're trying to look for an angle that is greater, that it comes in and looks like this, where this is theta 2 is equal to 90 degrees, and this is theta 1. All right, and we're trying to find out what this is, what angle this is. This is also called the critical angle. Okay, so I guess you could say theta c is equal to critical angle. And that just essentially means that what's the angle at which theta 2 is 90. Okay, so that's what it means. What we know is that theta c is equal to the critical angle. That is a fact. And then if this were to keep on going upwards like this, what would happen to this resultant ray? And what would happen is if it were to keep on going upwards, so like let's say this light will come in like this, okay? What would happen is that this light ray would actually become refracted, actually would not become refracted at all. So there's no resulting ray. It would just become internally reflected. And that's the whole point. This black line right here, this is the concept of TIR, or total internal reflection, where you are greater than theta c, the critical angle, to the point where no longer is the light refracted outwards, it is just reflected internally. Total internal reflection. All the light is internally reflected, okay? So that's what's occurring right here. To apply this to a real life, or even like a problem that you would find inside of your physics, and I guess to better understand this whole concept, I can draw like a simple illustration to help you better understand. So this is something that is very common that we might see, in physics class or just mastering physics or any kind of problem. Let's say we have up here, we'll just say air, which is N is equal to 1.0. And then this initial medium is, let's say water, because I know the densities for both those. Water. N is equal to 1.33. Okay? Let's see, we have those. And as we know, N1, N2, N1 is always greater than N2. Okay, that's a key component. So I guess we're looking for this angle right here. So we know that this is 90. So theta 2 is always going to equal 90. We're looking for this angle, which is theta c. Okay? So what we're going to look for is theta c in this portion. And what we can do to solve for that is something that we've used, and you will use, very frequently. And it is something called Snell's law. Snell's law. Okay? Which is N1 sine theta is equal to N2 sine theta, and just theta 1, theta 2, and then that's what it is. And theta 1, I guess we can initiate as the critical angle as well. Okay, so to plug everything in, we have 1.33 sine theta is equal to 1.0 times sine 90 degrees. Okay, and what we know from basic trigonometry is that sine of 90 is equal to 1. Okay, so now what we have is 1.33 sine theta c is equal to 1.0. Okay, divide 1.33, 1.33, and then what we now have is sine theta critical angle is equal to 1.0 over 1.33. To get rid of a sign on one side if we're trying to find an angle is to actually just take the inverse sign of that. So now that we can cross that out, we have theta c is equal to sine inverse of 1.0 over 1.33. Okay, and just give me 1 second. I can type this into a calculator to get the exact angle. To do, let's see. And if you typed it in too, you will also get approximately 48.8 degrees. Okay, just want that to stand out. All right, and so this is what we call the critical angle. So in this instance here, in this instance up here, we can now say that this is 48.8 degrees. In both of these, in any kind of critical angle dealing with air and water. All right, and what total internal reflection basically is any angle that is greater, so we just say than 48.8, some arbitrary angle, any angle that's greater than 48.8 will result in what we have right here, which is total internal reflection. So there is no refraction across parallel, there's nothing going outwards. All we'll have is internal reflection. And that's all that we see. That is the concept of total internal reflection, basically, in a nutshell. And if you want to apply it to anything more, like something that we use every day, is something called fiber optics. And what all it does is basically, science is made to the point where this is, as you can say, a cable. This is a cable, right? We have air out here, and then we have, some other medium. The light basically travels like this to the point where the angle that we have, the critical angle, it is greater than the critical angle that it comes in. So instead of anything coming outwards or refracting parallel, the light simply bounces within the cable. And that's actually how we use, I guess it's commonly used in telecommunications, and that's where this concept comes from, where if anything greater than this critical angle, and in this situation that we just did, anything greater than 48.8, it becomes internally reflected, where the light simply bounces off within whichever medium it is started in.